Okay, this is Module 2 from Week 8 on Association to Causation, and this module is on selection bias. Let's talk for a second about internal versus external validity of a study. So we've used those terms a few times this semester, but I don't know that we've talked about them specifically. So the contrast here with internal validity, an internally valid study is one where we're confident that we've measured what we've set out to do. It's a correctly specified and measured study. And we also mean by that that it's free from systematic error, which we also call bias. And internal validity is in contrast to external validity, which has more to do with the generalizability and the extrapolation potential of the study. So to whom can we generalize these results? And to some extent, internal validity and external validity are trade-offs. But here today we're mostly talking about internal validity and specifically sources of bias around selection of our participants in our study. So we think about error. There are lots of different ways error can be introduced into our study. Some of it is random, and some of that's just how the measurement tools we use, the scales, the psychological scales, the weight scales, all the random error that's introduced when we measure anything. What we're talking about today more, and there's not much we can do about that. We can acknowledge it. We can try to analyze how bad it is, but there's not much we can do about it. Systematic error, on the other hand, which is also called bias, we can do something about. It's difficult. Schlesselman calls it here any systematic error in the design or conduct or analysis of a study that results in a mistaken estimate of an exposure's effect on the risk of disease. We're going to talk about three main categories of bias in this set of modules. This first module is going to be on selection bias. We have one on information bias and a third on confounding. And Grimes and Schultz, in the reading that I posted for this week, calls this bias, just something different, quote unquote different, that distorts the planned comparison. So as you read studies and construct your own, think about, is anything different happening here between groups or across groups that's introducing some non-random error or some bias. So let's focus specifically on selection bias. And selection bias rears its head when there's an absence of comparability between groups being studied. It may be due to procedures that we use to select or exclude our subjects. It may be differences between participants and non-participants that we haven't anticipated or measured. Or it may be differences in follow-up. We talked about loss to follow-up or dropout rates or attrition that make the remaining group not the same as the group we started with. So selection bias first comes in at the beginning of a study, and we think about, so what's causing it? Well, individuals have different probabilities of making it into our study, and those probabilities may differ across exposure groups, and they may differ across outcome groups or potential outcome groups. And the result of that kind of selection bias is that our observed association is different from what's actually true in the population of interest, and we may or may not even know that. So I'm going to walk through a few examples, and as has been the case in the past, the example is based on a world in which we could actually see the true underlying characteristics in the target population, which of course in real life is very hard. But in all of these slides, on the left-hand side you'll see the target population. In the middle there'll be a table of selection probabilities. So how likely is it that this group and this cell through the selection process ends up in the study population. And then we're going to calculate some different measures from the study and see if selection bias is present. So in our first example, we're just doing a very simple cohort study. It's hypothetical with a 50% participation rate. So of the 1,000 people in our whole target population, every group, every cell, exposed and unexposed, diseased and not diseased, has a 50% probability of making it in. Again, we would never know that ahead of time in our cohort study, but pretend we can observe the world in that state. If that's the case, if there's a similar selection probability, an identical selection probability for all 4 cells, we'll end up with this distribution in our study of diseased and not diseased and exposed and not exposed. Over here we've calculated cumulative incidence, exposure prevalence, an incidence ratio and an incidence odds ratio, and just a difference in cumulative incidence for our exposed and unexposed group. Now I'm going to encourage you to pause the lecture and just take a little bit of time to work with this 2x2 table and calculate the same set of measures for the sample that we've already calculated for the target population. And when you're done with those, you can pop on to the next slide. Now, as you may have guessed, if these selection probabilities are the same, you're actually going to end up with identical incidence and exposure and association measures. So if selection isn't related to exposure or risk of disease, then we're going to have unbiased measures of association in our study. Let's take an example where the folks who are coming into the study are worried about their risk, the worried at risk sample, and it's a cohort study. So the exposure we're interested in is a family history of colon cancer, and we're going to measure incident colon cancer as our outcome. You could imagine that subjects who have that family history and are therefore maybe worried about their susceptibility or their risk of cancer might be more likely to agree to be part of the study. And let's see what happens if that's the case. So same population again. Now, the folks who are exposed have a 90% chance of making it into the study. The folks who aren't exposed, only a 50% chance. So now we've got a different 2x2 table here for the folks that end up in the study. Same set of study measures in the target population. Again, I'm going to encourage you to use this 2x2 table to calculate the incidence and exposure prevalence and association measures. And maybe you were surprised or maybe you weren't, but it turned out that our incidence ratio and our incidence odds ratio are actually the same as they are in the underlying target population, as is our cumulative incidence difference. Now, of course, we get a different incidence rate and a different prevalence, but when they are calculated out into our association measures, those end up the same. So as long as even though there's differences between exposure and unexposure in our selection probabilities, they don't differ across disease status, and we actually end up with unbiased measures. Okay, in our third study, we're going to look at something called the healthy worker effect, also a cohort study where the exposure is coal mining for 5 or more years, and our outcome is all-cause mortality. And in this design, we're going to select those who are currently employed as coal miners and compare them to a random sample of the general population. So, let's think about that. Are there going to be some subjects who have gotten that same exposure but are not likely to be selected? And who are those people? Think about that for a second. All right, well, here's our selection probability in the middle here for our same target population. Okay, what do we see different? Well, we see that this cell, which is our diseased group, or those who will die as part of the cohort study, and our exposed group have a lower probability of making it into the study than the other 3 cells. So go ahead and calculate these out, and let's see what we get and why. So our cumulative incidence and our exposure prevalence are a little bit lower than in the target population. Our incidence ratio and our incidence odds ratio and our cumulative incidence difference are all what we call attenuated. They're all closer to 1 or closer to 0 for the cumulative difference here. They're basically underestimating the association between coal mining and mortality relative to our target population. And why is that? Well, it's because the folks who have been exposed but are going to die aren't making it into our study. They maybe are too sick after their 5 years of coal mining work to still be working, or they've actually died already. So what we're left with are the healthy workers who've been exposed, a higher proportion of them who aren't going to die, and it's going to make that coal mining mortality relationship look smaller than it actually is. So these are going to be biased estimates when one of these cells differs from the other 3. All right, 2 more quick ones. A hospital-based case control study. This is taken right out of Gordis. You can go revisit it there if you like, where our exposure is coffee consumption and our cases are patients hospitalized with pancreatic cancer. Now, who are we going to have for our controls? Well, in this case, the physicians who are working with, treating the pancreatic cancer patients who are cases, they're going to recruit their other patients who are in the hospital for another condition, not pancreatic cancer, as their controls. All right, think about that. Who treats pancreatic cancer? What kind of clinician? And what other diseases might they treat? And might patients with those diseases have coffee consumption patterns that differ from the underlying source cohort? And what's that going to do? Well, we've got a cell here that is different from the other 3 cells in terms of selection probability. So our folks who are exposed are coffee drinkers, but not diseased from the target population have a lower chance of making it into the study. Why is that? Well, probably the other patients of our pancreatic cancer docs are also cancer patients, and they're probably sicker than the underlying general population. So now we're in a case control framework, so we can only measure prevalence of our exposure in our controls in our cases, and an odds ratio. There's no incidence to calculate here. Go ahead and calculate these, pausing if you need to. In this case, we actually see an inflated association because we see a lower prevalence of our exposure in our controls than is probably the case in the target population, and so our exposure odds ratio is actually higher. Now it looks like coffee is associated with pancreatic cancer more than it would have been otherwise if there hadn't been selection bias in who was chosen as our controls. So we would consider these a biased odds ratio. Lastly, and we seem to have lost some font size here, differential participation rates from a case control study. In this case, it might happen if the cases identified for a case control study are more likely to participate because they think some good might come of it for them or for other people who share their disease. And that's different from controls who we have a little bit harder time recruiting. In this case, selection is only on disease status. So within the diseased folks, we see 90% participation for both exposed and unexposed. And in the non-diseased state, we see 70% participation, again, for both exposed and unexposed. Again, a case control setting, so we're only going to calculate exposure prevalence and exposure odds ratios. And where do we end up? The same. Hopefully you guessed that at this point. So participation was selective on disease status, but within disease status, not by exposure. And that actually leads to unbiased odds ratios. So just some conclusions around selection bias. So if selection of participants on the basis of either exposure or disease is dependent in some way on the other dimension, that's when we're going to worry about selection bias. And you'll see that in the 2x2 table of probabilities if one cell is an outlier. Now, how do we know about this in real life? It's a challenge because we don't really know whether the causal parameter, the exposure factor that we're interested in, has some selection bias that we don't know about. So we usually have to guess about it. We need to model sensitivity around it. What if participants were selected and we didn't observe that? How different would our answers be? So I'll show you a quick example of that in terms of differential loss to follow-up. But you can do the same kind of analyses for selection bias as well at the front end. So here's a cohort of 1,000. Some are exposed, some are not exposed. We have similar loss to follow-up, so 14% in each case, leaving some other folks to be analyzed, some of which get diseased and some of which end up not diseased. Well, how should we analyze that? What should we do with our loss to follow-up people? Well, we can bound our estimates by looking at 2 different states. In one state, everyone who was exposed but lost to follow-up developed the disease, and at the same time, no one who was unexposed but lost to follow-up developed the disease. So this is a hypothesis sort of in favor of an association. So we'll make it as extreme as possible in favor of an association. Then you can redo the analysis and say, okay, we lost a bunch of people. Let's assume the opposite for all of them. So none of the exposed but lost to follow-up folks developed the disease, and all of the unexposed but lost people developed the disease. So these are both conditions that contradict our hypothesis of association. And you can see how much the association measures move. Maybe your loss to follow-up is small enough that those differences in these 2 extreme outcomes aren't that different. Maybe you completely flip them and you actually reverse the association when you reverse these 2 extremes. That's very helpful sensitivity analysis to do. Okay, how do we figure out and hopefully minimize selection bias? Well, of course you want to keep non-response as low as possible. and attrition. If you're going to have non-response, if you are recruiting people into a study and they're saying no, if you can get any information about them, are they different in age, in gender, in anything, in attitude, in exposure, that's very helpful too, because you can at least say our respondents are different from the general population in the following ways, and it is or is not differential on outcome or exposure, depending what you're looking at.